Morning, everyone. Hopefully, everyone's having a good week. Um, we're going to sort of move on with wrapping up our discussion of earthquakes and seismic hazards today. And then before the end of the lecture, we're actually going to transition into one of the more common natural hazards associated with earthquakes in terms of tsunamis. Um, so just to recap here, we talked about where earthquakes occur. We talked about some of the characteristics and nomenclature around earthquakes. And we also talked about some of the hazards that are associated with them, both from naturally occurring earthquakes and also human-induced earthquakes, including the likelihood that human-induced earthquakes would occur by various activities in light of things like wastewater injection and subsurface testing of weapons and things like that. What I really want to talk about in a little bit more detail before we moved on is actually what are the issues related to earthquakes. And this is where we left off in the last lecture. I spent a lot of time talking about ground shaking from the R waves and ground rupture. And in a sense, this is really the most common hazard in which we sort of face in terms of earthquakes, which can cause major damage to infrastructure, buildings, and can often lead to major loss of life. I showed you some pictures from a major earthquake in Mexico City, and that's not an uncommon scenario. But then we started talking about this right from the last class. Liquefaction can also be an issue. I'll take you through some examples of that in a moment, but that's where poorly sorted or unconsolidated, unlithified sediments can actually, and the pore waters and fluids in those grains can become mobilized by the ground shaking. Landslides, unstable slopes that can collapse and fail during these issues can be another major vector for damage and loss of life and property related to earthquakes, and often fires. We talked about this as well just a little bit. That in many cases we can see that fires, particularly from the rupturing of gas pipelines, can cause major disruptions. And in the case of the 1906 San Francisco earthquake, that was one of the major losses of life and property were tied to the fact that the existing, pretty new age at that time infrastructure was actually damaged and ruptured, causing petroleum and natural gas to leak and eventually burn. The other factors which can influence people, we'll talk about this a little bit more in tsunamis as well, is that it can actually cause regional changes in the groundwater. If you actually move the surface, the water will try to reestablish an equilibrium, and that can change the location of groundwater and ground elevation. That can have influences in terms of taking water and pushing it below an area where a well exists, so there's no longer viable access to water. Or in other cases, it can cause flooding in areas that are unchangeable. I mentioned the earthquake in the the Missouri area back in 1811, 1812 that drained church bells in Boston earlier in this earthquake lecture. But one of the most historic aspects of regional changes in groundwater and ground elevation actually caused the Mississippi River to flow back from the Gulf to the north as a result of that, and permanently changed groundwater flow rates and river flow rates for a few months until the system reestablished equilibrium and some engineering was done to fix a few of the problems. So this can lead to major salinization events where the water can become contaminated with seawater and stuff like that as well. Tsunamis, which we'll talk about in great extent at the end of the lecture, and disease, particularly waterborne diseases and infectious diseases. So the waterborne disease, this will be a theme of almost all the natural disasters. Most people do not die from natural disaster. Most people die from waterborne diseases, infectious diseases, and violence after one of these natural hazards. We'll talk about that more in detail as we move on throughout the semester, but particularly waterborne diseases, you can imagine if you're disrupting gas pipelines, you're also going to do things like disrupt sewage pipelines and other infrastructure that can put things like cholera, fecal coliform, and other vectors for disease into the water. It can change water patterns, allowing mosquito populations to expand rapidly. And also, obviously when you're in situations people don't have access to clean water, sanitation, and hygiene, or what we call WASH, infectious diseases can spread much more rapidly. As well as violence, people sort of, try to deal with managing and obtaining resources during those times. So I'm going to just very quickly go through each of these in a bit more detail, and before we move along. And this gives you a perspective. The ground shaking rupture, the shaking is a little bit hard to hard to show. There's some images if you want to find some videos of that, you certainly can. But I wanted to give you a sense of the land ruptures. Often here, we're showing a vertical component. This situation, this individual is just over 6 feet tall, and that's a scarp, fault scarp that's formed during one event. So imagine you have a home with a foundation or a building with a foundation that intersects this fault, fault at the time, and you see a 6 foot offset in those areas. That can be pretty hard to imagine a building actually withstanding that. So clearly, shaking, ground rupture can be responsible for significant damage, earthquakes. It's not uncommon for the earthquake damage to be in the billions of dollars when major ones hit, and that's something we really have no way of avoiding more broadly. For perspective, the 1989 Loma Prieta one, this is in 1989 dollars, was magnitude 7.1. That was about 5 billion. If you're thinking about today, that'd be something on the order of, I think, $8.5 to $9 billion of damage from one earthquake event. But for example, the Northridge, LA, magnitude 6.7 in a more densely populated area, and also in areas with a little bit higher real estate values. That one spanned up to $40 billion. So outside of the loss of life, infrastructure, and potential for secondary effects like various diseases, these can have major economic, like all the natural hazards, major economic implications. So I think for the case of liquefaction, it's easier to show a video to describe this, and it's really a transformation of, again, sediments that are filled with pore spaces are filled with water, or water saturated sediments from a solid to a liquid state. And this video hopefully will play and also give you a perspective as to the liquefaction process. And that is the town where Kobe beef comes from. I'm not sure why the volume's not playing. So I guess the first thing I want to point out is that you note that the water is sort of all over this area here. The water can basically migrate up through the pore spaces and above the solid grains. The other thing is you actually see the grains are sort of lost. You don't see any more soil at the surface, and this can create some this doesn't occur uniformly and create some variable sort of pseudo sinkholes. Can happen pretty rapidly and actually do a great amount of devastation. So that can happen on pretty large scales. Keep in mind, this can, these earthquakes, a magnitude 9 earthquake is something like multiple decades of, multiple years, sorry, of energy usage. So these can cause a lot of water to sort of soil sort each other out. The water eventually will just dissipate back into the ground, but leaves a lot of sinkholes and damage behind. On the topic of earthquakes related to landslides, oftentimes the shaking of the earthquake itself, the R waves, triggers landslides, but just destabilizing slopes. There's you would call this a hill slope failure, and obviously if you are living in an area where this material comes down into an urban area, this can cause extensive loss of life and property damage. There's some really big examples of this, particularly near seismic activity related to volcanic activity, and also there were also pretty large landslides attached to the Mexico City example we showed in the last class. So if you're in the wrong spot, these can be extremely devastating as well, and do a lot of damage to property and life. So this is actually an example. It's pretty large scale here. This luckily was not near an urban area or population center at all. This is from a magnitude 7.9 earthquake, and triggered a landslide on the side of one of these volcanoes that I think, if I remember, there's something about 2,000 square acres that were covered by at least 10 meters of rock material. So you can imagine that's a pretty devastating event. This example is actually in El Salvador, and this one was in an urban area, killed 500 people in an earthquake in 2001. So regarding to fires, I think this one's fairly obvious. Gas lines and power cables. These are sort of new age problems with earthquakes. Obviously, these is only around for a few hundred years. During the 1906 earthquake, 80% of the damage was actually from the fires rather than the quake or the landslides or anything else like that. So this is an example from the in the Marina District of San Francisco, if you've been there, from the Loma Prieta earthquake in '89, where I think it was pretty much about a city block and a half ended up catching fire related to the rupture of gas lines and the downing of power cables. Today, most urban areas, whether they have a high earthquake risk or not, try to put the power cables below land surface in conduit, so there's some space around them, so if they get shaken, they're not going to get ruptured. But the gas pipelines obviously require a much tighter fit, and are more prone to brittle failure and rupture. So that problem really has not been mitigated at all. So there's a question a lot of folks ask, at least when we're able to be there in person together and have this more open discussions, is can we actually predict earthquakes? And the reality is, it's been a pursuit of earth scientists and generalist scientists for a long time. But the reality is we're not really there yet. And I'm not personally confident that we ever will be. What we are really good at doing is cataloging where seismic activity occurs, cataloging the amount of seismic intensity that occurs in specific areas. And as a result, we typically are making hazard maps where we can provide reliable information to citizenship as in terms of what the risks are in a given area. What can this do for you? In reality, you can make an informed decision about whether you want to live in an area of earthquake damage, with potential for earthquake damage. You can choose to avoid living in areas where you're in valley bottoms with alluvium and unsorted sediments. You can try to relocate or locate your houses and property in the locations where that's not going to be relevant. As I sort of don't advocate for this latter point, but you can also consider buying things like earthquake insurance. So if a natural disaster like this influences your life and property, you can have some sort of fallback. In reality, the first two are far more important in terms of sustainability than the latter. It's sort of a losing proposition, which will be a theme of our course as we go on, of people who try to live in the particularly as it relates to tsunamis, for example, or hurricanes, try to live near coastlines is beautiful, even though it's not really a sustainable plan. So really, what I wanted to get you a sense of is what goes into making these hazard predictions. The most important one is sort of old school geology. This is actually mapping where faults are located, identifying areas of faults, identifying paleoseismic activity, understanding how much damage is acutely related to the P&S waves near the epicenter of that earthquake. It doesn't necessarily help you predict the R wave, the ground shaking waves we talked about, but that's an important mechanism is knowing where the faults exist. Obviously, the paleoseismicity to determine where things have occurred. Now, these aren't done by, imagine, trying to recreate seismic activities. The way we actually do paleoseismicity is dealing trenches, excavators along faults, and seeing how many different events have occurred and looking at the scale and magnitude of those events. So typically, those efforts are ground truth by a known event of a specific magnitude, looking at how much offset and debris flows during that time, and then basically reconstructing the record by going back down through all the seismic events and getting a history of what the risks are over time for earthquakes of various magnitudes in a given area. One of the newer ways, and I think actually a much more successful way, it's just a lot of great promise and is a really core strength of Ohio State University more broadly, is something called geodesy. And this is basically determining how fast the Earth's plates are moving, in what directions, and making predictions of where stress is building up on the surface of the Earth. We can, we know stress eventually, as we saw those maps, those diagrams, sorry, earlier in the lecture on seismic. It's stress versus strain, and eventually, as stress accumulates, strain will occur, and that strain or deformation will lead to earthquakes of specific magnitudes commensurate with the amount of strain that stress that accumulated. So what is geodesy? I'll take a moment to just explain this. Geodesy is largely use of global positioning satellites, GPS, or direct satellite imagery. Now it's often done additionally with unattended aerial vehicles, UAVs, and other mechanisms to track the relative positions of the Earth and the accumulation of stress. But most of this is really high-tech stuff done with satellites that actually directly monitor global positioning and deformation near the surface as a predictor of stress to understand how much strain will occur during a particular event. And then, of course, is also the role of seismology isn't gone away. The past seismograms that tell us how much activity occurred in a given area, and it lets us understand the level of activity and the typical level of magnitudes are often useful for predicting if there's a precursor to earthquakes that are building up in certain areas. So those four factors lead to this risk map you see here on the right. And those risk factors, of course, as we mentioned earlier in this earthquake discussion, can be pretty variable across different parts of the country. Many times in locations where people don't really think about them, like Charleston, South Carolina, and the Mississippi River here, stretching from basically Illinois down into Arkansas. But the reality is, most of them are along major plate boundaries. Particularly the most active one is along the boundary with the Pacific plate. So while we do know those are the highest areas, both in terms of likelihood and probably in terms of absolute magnitude over a period of time, remember that these earthquakes within plates or intraplate earthquakes can have magnitude up to around magnitude of 8 and do significant damage over large areas. So in terms of short-term predictions, this is a big pursuit. It's still an active area of research in the geosciences. And there's a lot of work by using seismic and geodetic methods to examine foreshocks that are basically an increasing understanding of what foreshocks look like that occur before a major event. The reality is there's also a huge human economic cost and other risks associated with relocating populations in advance of these. We don't have it down very well, just like volcanic hazards and tsunamis we'll get to a little bit later in the semester. But there has been some limited utilization of understanding foreshocks in China by basically examining seismic, having a response, and actually relocating people out of the area, evacuating them as a result of foreshocks. So that's starting to be done. It's not very well adopted, and the reality is, as much as we like to think about it, it's not practical in major urban areas, even if we wanted to. Just like you think about Hurricane Katrina, many people were able to get out. Not everyone can get out, and obviously, there's a sort of an asymmetric influence on, from a social justice perspective, on less affluent members of that society. The one that's been more commonly used is basically predicting, as I alluded to with geodesy, predicting how much strain is building up where deformation is actually starting to occur on land surface. Really good in terms of seeing things on the couple day to week schedule, but not necessarily very good on a few hour schedule. It's often what you need. So just like foreshocks, it shows promise, but we're really not there yet. The one that's been more commonly successful and is now instrumented in a group of detection systems along the San Andreas Fault, for example, is actual remote continuous monitors of specific gases. Radon and hydrogen are both released very efficiently when rocks start to break a little bit subsurface. When the stress first starts to begin, there's something called cataclysage, which is basically the breakdown of minerals at depth, and that releases radon and hydrogen. Same thing here. The reality is the gap between when those are emitted and when they're sensed can be days, can be seconds to months, and as a result, like the other techniques, it's very useful for giving us some information, but not necessarily reliably relocating a major urban population for some indeterminate amount of time between seconds to months. So it's hard to sort of utilize these techniques to move populations around. Excuse me. The other component is more historical, which is identifying seismic gaps. We know there's a fixed amount of stress on plates, and we know that on the aggregate, stress and strain will reach an equilibrium. So if we identify areas where there's been seismic gaps, there hasn't been strain commensurate with the amount of stress, we can make prediction that earthquakes are due. You often hear people talk about this in San Andreas, that LA's due for a big one. You hear people say things like that. It's not exactly accurate, but it's sort of tied to these seismic gaps where you look at areas where there hasn't been an accommodation of movement for a period of time, and you recognize that stress will be accommodated for at some point in time. And obviously, we don't have a mechanism for controlling that, but what we like to see in areas with active faults is that there's a whole lot of micro and small earthquakes, and not a lot of seismic gaps that build up a lot of stress leading to a big earthquake event. We talked very early in the semester about the earthquake that hit Haiti in 2010, and that plate boundary of the Caribbean plate is a perfect example of an area where we see a series of seismic gap buildups, where we couldn't predict when, even on the monthly scale, but we certainly knew that the Port-au-Prince area was due for a major event like that, based on the amount of based on the length of the seismic gap, the amount of stress that it built up during that time. So, you can think about this holistically. Should we be creating maps of seismic gaps and involving urban planning? The reality is, we'd like to think like that, but we often don't have that control in presenting that. So I think that the key thing I'd send you back to is, again, considering, in local context, even if you're in California, even if you're in the Bay Area, if you're living in on top of solidified rock rather than alluvium, you have a much greater chance of avoiding major damage than you do by being down in valley bottoms and alluvium. Ironically, this is not actually a joke, although I find it kind of funny. One of the best ways that people have used to predict earthquakes has actually been anomalous animal behavior, and this is sort of anecdotal, not my own anecdotes, but anecdotal. It's been identified across a variety of different cultures. There's a lot of utilization of this in China for predicting this, but there's anecdotal reports that hens refuse to lay eggs on mornings where there's earthquakes occurred, that you'll see rats climbing up telephone poles and climbing on wires, that the dogs will just be out sort of jumping around, barking unusually. And my personal favorite is that pigs on a roof. There have been a lot of reports that some of the pig farms that have the little ramps up to the roof so the pigs can sun themselves, that there have been reports that before, within a few hours before a major event, the pigs will often go up on the roof, which I guess may or may not be useful information. Most importantly, as one of my Chinese colleagues told me, it's also true that the pigs go up on the roof on a daily basis, sun themselves, but maybe some more of them go up when an earthquake might occur. I don't know if these things are really predictable methods, but there's certainly a prevalence of stories like this in a variety of cultures around different parts of the world. And it does make sense that, for example, dogs who are more attuned to the environment and can have better sense of hearing could sense some of these sort of low frequency waves, lower frequency R waves, like that are minor shakes. But, clearly anecdotal, and in reality, not obvious that the entire urban area is going to relocate to solid ground because there's reports of a pig on a roof anywhere. So, in summary, earthquakes are a result of faults in the Earth's surface. Rocks can either slide. Rocks on either side of the fault can move up or pass across each other. Clearly, the stress builds up to cause the strain or the deformation, and that amount of stress and strain are commensurate with each other. So, when we want to talk about where the Earth is, where the earthquake is, the location is the focus. The area above that, where it intersects the surface, is the epicenter. I know you all know this very well since you did so well in the exam. And the key thing to remember here is that there are three types of waves, all different properties. P and S waves are generated in the subsurface and basically are can travel through all materials in the case of P waves. And the S waves only travel through solid rocks. And R waves are produced very near the surface, and that's actually what does most of the damage. And that, you know, human planning can certainly exacerbate the amount of damage from earthquakes. We talked about this in terms of poor construction in Haiti really early on in the semester, but there's clearly from a societal perspective and urban planning perspective, there's just too much building on unsuitable land, construction of dams, reservoirs, and you know, major buildings in areas that, you know, where there's underlying alluvium that can cause damage, you know, clearly that there is evidence for micro earthquakes and small earthquakes, microseismicity and small earthquakes caused by disposal of liquid waste in subsurface. So humans can, in effect, influence their own environment. I guess what I'll say is that, you know, for this, you know, for these components, for dams, reservoirs, and buildings, we've made great progress in most of the world in the last, you know, few decades in terms of actually driving pillars down into you know, into solid bedrock and putting moorings, stuff like that, that keep the buildings better. So it's been handled a lot with modifications to buildings and requirements for building, you know, more robust buildings in areas of high earthquake risks. But in reality, it's a challenge. One throwaway idea before we move on to tsunamis is that there are people proposing that, you know, if we've learned what we learned from the disposal of liquid waste, that by putting water into the wastewater into the subsurface, we can cause these microquakes, which basically just release, help release the stress that's accumulated in an area. Some people are proposing that we might want to consider actively doing this in areas to mitigate stress, to remove those seismic gaps. So you see a lot of stories about that occasionally on the news and in the popular press. Every couple of years you hear a story about that. I'm not terribly optimistic, just because, you know, you don't really know how much strain you'll release when you or how much stress you release when you introduce those fluids. But that's an idea that people are passing it about. So I'm going to transfer over to the tsunami lecture, unless anybody has any questions. I'm going to move along here. So the one component of earthquake hazards I didn't really spend any time on was related to the occurrence and impacts of tsunamis. And you know, I'm basically gonna treat them as their own form of natural hazard. They certainly can do a lot of damage. They're quite graphic. You can see the amount of you know, water overflowing this coastal area. You know, you see the boat here. We see a pretty large wave hitting. This is Japan in this case, with large waves. And you know, I think it's funny, just not funny, ironic, I guess is the better way of saying that. But tsunamis have a really prominent place in poetry and literature, and are often talked about as sort of being these, you know, events that people, you know, have long-term fears of. I guess tied to fears of drowning. But they're actually quite complicated. They occur on pretty massive scales and can do quite an amount of damage. What I'm going to do first, assuming the video works, is I'm going to show you a video of the earthquake and tsunami from 2011. Basically, this is the earthquake tied to the series of earthquakes that led to the Fukushima damage. So we'll start with that, just so everybody gets a sense of the scale and damage caused by one of these earthquake events, earthquake-induced tsunami events, and then I'll go through some of the specifics about how this actually works to follow.
Off the coast of Sendai in northern Japan, a succession of extraordinary waves, some said to be 10 meters high, accelerate towards the shoreline. The menacing band of white bears down on the land. Striking land, the massive surge turns into a black wall of water, unstoppable by man-made structures. Houses and barns are consumed, vehicles lifted up and carried away.
Keep in mind here, these are actually entire buildings and you know, trucks that are being carried. And notice how far that is from the coastline. These can do pretty catastrophic levels of damage and really transport a lot of energy.
Despite a tsunami warning, many are caught out. To the right of screen, some motorists drive away, but others on the highway seem unaware of what's approaching across the field and have little chance of escaping it.
And so most people here don't really even know what's happening, obviously. How could they? It's almost instantaneous.
Water pours over the elevated section and they become part of the debris. A swirling kaleidoscope of broken buildings and floating cars.
I mean, could you imagine what your strategy would even be in this scenario? I mean, you're just basically hold on and enjoy the ride.
These images clearly capture the power of the tsunami, but from above it's hard to calculate how many people are caught up in it. Only those on elevated land could possibly avoid it. And as it continued to move further inland, it still had the power to carve its own path and continue to carry tons of wreckage.
Obviously, it's easy to see, major ship, buildings, debris, and all this damage. One of the hidden implications of a tsunami that I wanted to point out to you here is recognize, you just think back in your mind as this video's unfolded about how far from the coastline we are, and recognize that this is actually all seawater. So one of the implications, in addition to all these damage and debris, is of course you're actually, in this picture is perfect place to see it, you're eroding agricultural soil, so key soil for growing crops, but you're also basically salting the earth, right? You're putting salt water on top of these areas, which percolates into the ground and actually causes salinization and makes the water in these areas unsuitable in many cases for drinking, depending on how much salt water is added. So, some of the effects besides the obvious, physical damage, the unlikelihood of anybody to get out of an event like this alive, the reality is that the long term is you've lost your soil profile to grow food. Your water now has been contaminated to the point where you probably can't use it for drinking. At least as that, salt water transmits itself through the groundwater, which we'll talk about later in the semester. But my point here is that it's really almost unfathomable to recognize the myriad of ways that an event like this can cause damage and the scale of it.
A huge trawler rides inland. In an instant, normal life is invaded by a sea of chaos. Gas and electrical faults caused by the earthquake set off fires. And as the debris is piled high, the flames ride on the water as it presses forwards on its relentless journey of destruction. It creates an apocalyptic scene across swathes of land. Right of screen, a vehicle can be seen trying to speed away from the wall of water, but it's trapped.
This is the vehicle they're
Further
talking about.
right,
Clearly nowhere
a
to go.
dot of a person can be seen trying to outrun the wave. The pictures don't show whether they made it. This footage, filmed from a hilltop, shows the tsunami's terrifying power. An entire town is being turned to rubble.
So you get a sense of the scale of of potential for coastal erosion as well, and not just the physical damage, not just the soils for agriculture, but the actual loss of cliffs. And
back out at sea, some boats try to ride the waves. Here, a craft is at the mercy of a massive whirlpool. At Sendai Airport, this was the view from the terminal as the wave enveloped its runway. Would-be passengers sought refuge on the roof.
Excuse me. One of the things we don't necessarily talk about is, I think I've lost the video there, is the amount of damage that actually occurs when the wave and the debris comes back out. That can often cause a secondary loss of life and damage.
The destruction is plain to see, but it will take time to calculate the loss of life. Early indications suggest this tsunami has taken a heavy toll. So far, authorities say several hundred bodies have been found along the coastline. Once the water settled, it became clear most of the 1,200 homes in the rural area had been hit by the wave. Clearly, many people are now trapped in their homes. An unknown quantity may be injured and desperate for help. But the armed forces say 60 to 70,000 people in Sendai have been evacuated to shelters. In minutes, it seems, hundreds of lives have been taken, homes destroyed, and whole region churned up by a force of nature. Jason Farrell, Sky News.
So that's a fairly devastating video to see, but it gives you a sense of the incredible amount of damage can be done by a tsunami. So what we're gonna start for a few minutes here is getting into the process that actually cause these events. What leads to tsunami, and the most common vector for a major tsunami is actually related to large earthquake events, particularly related not just to the shaking, but actually displacement of rock, or that fault scarp formation can cause major offsets in water and cause really large waves. Obviously, just like the earthquake events themselves, the magnitude of the earthquake is commensurate with the amount of or the potential for tsunami related damage. You know, for perspective on this, I didn't really talk about this. We talked about the earthquakes and risk maps of the United States, but 70% of the Earth's surface is covered by oceanic plates. As a result, the vast majority of earthquakes actually occur in those oceanic plates, and more importantly, about 40% of the world's population lives within, I think it's 10 miles of a coastline. Those numbers might change a little bit over years, but the point there is that actually, even though we think of tsunamis as being sort of episodic events, they actually can do an incredible amount of damage, and it's one of the natural hazards where people have genuine risks. Maybe not quite as devastating as the video we just showed, but certainly genuine risks of hazards related to tsunamis. The other common mechanism of creating a tsunami is actually an underwater landslide. Those are often in themselves triggered by earthquakes. Sometimes they can actually just be slope failures where the slope builds up from sediments and just fails. But that mass of material being transported down to the bottom of the slope causes the water to shake. It's sort of like sitting in a bathtub and sliding down. The water will flow out and away and basically lead to a major tsunami event. Additional component is submarine volcanic eruptions. If this actually happens pretty commonly near volcanic areas where there's an underwater eruption. It basically emits magma, which becomes lava, obviously, but it also devolatilizes, and a lot of the gases that are present in those rocks are volatilized and kind of offset the water and cause the water to be displaced, causing tsunami events. And then, of course, this is the one that people have talked about in terms of the mega tsunamis. If you're into the Discovery Channel, and they're super volcanoes, mega tsunamis and whatnot. But there is episodic evidence of major asteroids or comets. If they hit land, they obviously cause an immense amount of devastation. But sometimes meteorites, up to relatively large meteorites and asteroids, can actually hit in the ocean and lead to mega tsunamis. And these are actually pretty insane levels of damage. These are about 100 times higher than some of the tsunamis known to be produced by earthquakes. But there is evidence in the rock record of tsunamis that are, that stretch up to 300-400 meters. That's a third of a kilometer high, which would, if you think about the map of the United States, would penetrate into something like Pennsylvania and the Appalachian Hills before it actually, the wave was stopped. So clearly, this event is something that's believed to be, is in a probabilistic perspective, it's thought to be random and very low probability, but of course, if it occurs, can be incredibly devastating. Key point here is there are evidence for these events episodic throughout the rock record and sedimentary record, of the Earth. So, a few examples of these major tsunami events. One of the more famous ones was related to a magnitude 9 earthquake in Lisbon in 1755, and it generated a tsunami that, together with the earthquake resulting fire, killed 20,000 people directly. Believed to be many more derivative deaths caused by the waterborne diseases and infectious diseases I mentioned as risk factors earlier. But for perspective, this tsunami actually crossed the entirety of the Atlantic Ocean, and in the West Indies, there were tsunami waves 7 meters high, and recordable waves in the Cape Cod area and stuff like that of 3-4 meters high from those tsunami events. Tied to volcanic eruptions, Krakatoa volcano actually erupted in 1883. Literally had a catastrophic failure. The top of the volcano actually collapsed and exploded into the ocean. And this collapse was produced one of the largest recorded tsunamis, over 35 meters high, that destroyed 165 villages and killed about 36,000 people that we know of. That's one of the key things about some of these early earthquakes, is that we don't really have good census and reporting data, so they're really estimates. And again, you can always consider it's going to be a multiple of that, of people lost to the long-term implications of disease related to those factors. Some other examples, although luckily not as devastating to the human loss. 1946, just after World War II here, magnitude 8.1 earthquake in Alaska produced a tsunami. Think about Alaska going all the way down the Pacific into the Hawaiian Islands. That had, I believe if I remember correctly, had a tsunami waves of about 10 meters high, and luckily only killed about 160 people, largely because Hawaii wasn't nearly as populated at the time. And then, of course, I think you all would be alive for this. Many of you are probably too young to remember it, but probably have heard about it. It was the 2004, Boxing Day tsunami, the day after Christmas, caused by Sumatran earthquake, where the tsunami itself killed about 230,000 people directly, with many more being related. We'll come back to this earthquake a bit more as we move along. And of course, here's the tsunami related to the magnitude 9 earthquake, 40-meter high tsunami, killed about 16,000 people, and obviously led to other major infrastructural damages, Fukushima and whatnot. So the first question is, how does this actually work? How does an earthquake, for example, induce a major tsunami event? And the key component here is that you have to see it's typically caused by an offset in the surface of the ocean basin. And what happens is that earthquake will cause a fault scarp to form. That offset will displace the water upwards locally. So often you can see, if you had a buoy or you're on a boat in this area, you can see an initial jump in height in the dozens of meters, for example. 100 meters is not uncommon. Luckily, when you're out in the ocean, you sort of can ride the wave a little bit. And the key thing here is that these waves are actually transmitted at incredibly rapid rates. Incredibly rapid rates towards the surface. So I'm going to show you here if it shows up, pardon my technical difficulties here. Apologize, I'm having a little problem here. But the key things here that in the deepest part of the oceans, this wave is going to move really rapidly, and it'll be spaced really far apart. It actually looks very much like a P wave, moves very quickly, very shallow amplitude, and transmits an incredible amount of energy towards the, away from the epicenter of the earthquake event. For perspective, these waves are moving at about 450 nautical miles per hour, which is not at the speed of sound, but getting that direction. And the important thing to consider, and what makes it really hard to predict them, or at least has for a long time, is that in the deep ocean, the spacing between waves, it can be incredibly long. The deep ocean can be really flat with waves being very slow, low amplitude, very long wave periods. As a result, the wave period can actually be as long as about 60 miles, which is not which is really a great distance. Even with relatively large tsunami events, only an amplitude of about 1 meter, or a higher swell, if you will, than normal. So as a result, you could be literally in the area right above the epicenter, and you may feel a little bit of wave. If you're displaced in that area, you probably won't even notice a difference at all. And as a result, most people out in the deep ocean don't even know a tsunami's there. As an anecdote, if you're out in a boat and a tsunami warning goes out, the best thing to do is to drive away from the land and drive to the deep part of the ocean, because the further out you are, the less likelihood you're going to encounter a tsunami wave, the more likelihood you're going to encounter one of these fast-moving low amplitude waves that won't do much damage. The key thing is that as this tsunami moves rapidly towards the land surface, it actually continues to gather speed. But as you can see here, the problem is that right here, the depth of the ocean is deeper. There's a bigger tub, if you will. And as you get closer to the surface, onto the continental slope, you'll notice that it starts to get lower and lower and lower. Basically, what we have is a mass balance problem, where there's a fixed amount of volume of water that's racing towards the continental crusts. And as you get closer to the landforms, that water basically has to increase the height of the water column in order to handle putting the same amount of mass through a smaller and smaller unit of area. And that's what causes the waves to get really high as they reach the surface. So, the key here is that the landforms, the continental margins, actually slow down the waves, but basically transmit that to a greater height of the waves, which of course cause a lot of damage once it reaches the surface. And of course, once it gets there, the devastation can be really quite profound. So the key things here is, as the tsunami nears the land, the water depth will initially decrease to accommodate the amount of water coming into that waveform. So one of the best indications that a tsunami is coming is you actually see the ocean water rush out if you're on the beach. The reality is you don't have very much time, so it's not going to necessarily help you survive a major tsunami, certainly. But initially near the beach, the water depth decreases. The tide appears to go out really rapidly. That rushing out of water causes the wave to slow down, but also helps it build height in addition to the mass accommodation. So these can be coming in relatively slow rates, but at really high, commensurate with what normal waves come into the land surface at, but very high, great heights, right? So the decreasing velocity also compresses the waves. So rather than having these 60-mile long gaps between waves, we can compress the waves so the tsunami is just boom, 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 and actually the waveform gets really small as well. All of these things contributing to increasing wave heights. So what I want to quickly show you, and then we'll wrap up after this, is basically a scenario of how the earthquake actually causes the event. You'll see here, this is the overriding plate. Here's the subducting plate. Typically in ocean settings, you have some sort of subduction going on. Subduction occurs, stress is building up. Stress is building up, deformation starts to happen. And then at some point in time, you'll see a major earthquake event or a fault scarp. And I'll just take you back here briefly. You notice that that's going to cause localized displacement when this faulting event occurs in the wave here, and sends it out in a sort of a conical pattern all around the earthquake epicenter. Actually, I'm just going to wrap up here rather than getting into the next aspect of the landslides causing tsunamis. I don't think they'll have enough time to cover that in 5 minutes. Just a reminder, sort of the recovery from the exam and the quiz, no worksheet due this week. Another one will post on Sunday at 5 o'clock and will be available for the following week. And we'll catch up on the key components tied to tsunamis as well as the end of earthquakes. If anybody has any questions, I'll stay on the chat for a few minutes, but or I'll sign back onto the chat with a few minutes. But I'm gonna end there. We'll pick up here on Friday. Hope everybody has a good week.